It's December 14th here in Rochester, New York, and today the sun will set at 4:36. The earliest sunset of the entire year already happened on December 8th, so why will the sun set earlier today than tomorrow?
Trying to answer this question will reveal some complexities about how long a day actually is. A good place to start is to ask a more straightforward question. How long does it take the Earth to rotate?
A simple way to answer is to look at a faraway star and measure the time it takes for the star to get to the same position in the sky the following night. If I were to do this, I would find that it takes about 23 hours and 56 minutes. Scientists call this measurement system based on the star's sidereal time. So where do the 4 minutes come from that give us 24 hours in a day that our clocks are based on?
Instead of using just any star as our reference point, let's pick the sun. A great way to measure the sun is using a sundial. If I were to measure the time between when the sun was at its highest today and highest tomorrow, I would get a new value of 24 hours and 30 seconds. So why does our time change based on our reference point?
While the Earth is rotating on its own axis, it's simultaneously rotating around the sun. Due to this extra rotation, the Earth needs to turn about 1 additional degree about its own axis each day to keep up with the orbit around the sun. It's exaggerated in the simulation, but it shows the point pretty well. This small difference accounts for the change between our new and old numbers for how long a day is. The 4 extra minutes means the Earth actually rotates 366 times in a year, resulting in 365 days.
Our new number is closer, but it still isn't the 24 hours we were looking for. In fact, if you were to measure this time for every day of the year, you'd get a different value every day. When you plot the values from every day of the year, the graph looks like this. Closer to answering our first question, why doesn't the winter solstice have the earliest sunset time? If one day isn't exactly 24 hours, then our clocks are going to drift slightly off of the sun. If this drift ever outpaces the days getting shorter, then the earliest sunset won't be on the solstice. And this is exactly what we see. Unfortunately, this doesn't quite answer our question of why the sun sets this way. Right now, we just have a funny-looking graph. The graph we want to understand is dominated by 2 main factors, the shape of the Earth's orbit and the Earth's tilt in relation to the sun.
The Earth doesn't orbit the sun in a perfect circle. It's much closer to an ellipse. A planet in an elliptical orbit will move faster when close to the sun and slower when it's further away. This change in speed means that the effect of the Earth rotating around the sun varies throughout the year. When the Earth is closer to the sun, the sidereal motion discussed earlier has more of an effect than during the summer months. The second concept is a little bit harder to explain, so I'll use this orange representing the Earth to help. Imagine that this black line is the equator, and this red line represents points where the sun is directly overhead throughout the year. You can see where the sun is directly overhead, represented by this glare. Because the Earth is tilted, as the Earth rotates around the sun, the point where the sun is directly overhead actually follows a line angled from the equator. This means that some points of the year, the sidereal motion of the sun is directly east-west, while at other points of the year, it has a north-south component. This means that sidereal motion is not always constant and varies based on the tilt of the Earth. With the mechanisms understood, we can try to generate our own version of the graph we saw before. First, we can find out that the effect of Earth's elliptical orbit causes about a 10-second deviation from 24 hours, peaking on January 2nd. This effect is best represented by this sine curve. The effect of Earth's tilt creates a more significant deviation of about 20 seconds that peaks on the solstices, meaning that it repeats twice per year. This can be best represented by this sine curve. By adding these 2 effects together, we can see we get the same exact graph from before. The small differences we calculated can lead to our clocks being 18 minutes off solar time, disregarding time zones. Because both of the effects we calculated are cyclical and repeat every year, on average, a day is exactly 24 hours. This doesn't stop large differences from building up within the year, sometimes outpacing the change in day length, especially near the solstices when it's shorter. And that's why the shortest day of the year is December 8th here in Rochester, New York.